Today we're going to look at infinite limits. What happens when x gets really, really big? Now, as x gets really, really big for x squared, you already know what your x squared graph looks like. And what we're thinking about is what happens to our y values as your x values get very, very big? Can you see from a parabola that that graph goes up forever and that your y values will be getting larger and larger and larger? So what we're going to do for a question like this is we're going to say the limit as x approaches infinity of x squared, we're going to say that it's equal to infinity. Now some textbooks, and I think your textbook sometimes does this, infinity is not actually a number. And so some textbooks will say that it does not exist because you can't actually have a number. But in this situation, you'll often find, and I'll ask you to do this on your quizzes and tests, that it's nice to say infinity because that tells you that you know that it's going up forever. That its end behavior as x gets large is that graph keeps going higher and higher and higher. As opposed to negative infinity, which also would not exist, but you would know it goes down forever. So the fact that we write the limit as infinity is giving us more information than just saying does not exist. So in this situation, what happens when x gets really, really big, right? Well, if x gets really, really big, it's going to get multiplied by -3, and then you're going to subtract 5. Can you see that that's going to be a really, really big negative number? Again, if we think of this graphically, this graph is a line with a y-intercept at -5 and a slope of -3. This is what the graph looks like. And we're asking, as x goes to infinity, positive infinity, what happens to our y values? Well, our y values keep getting bigger and bigger, but bigger and bigger negative values. So we would say the limit as x goes to infinity of -3x minus 5 is negative infinity. So the key thing is to decide if it's getting big, is it getting to be a big positive number or a big negative number? And now we're going, what happens when you put in a large negative number? Doesn't have to be x, so this one's the limit as n goes to negative infinity. First question, if you put a big number in there, will that get bigger or will it go to 0? It'll get bigger. So we already have a sense that our answer is going to be infinity as we get bigger and bigger and bigger. Now, is it going to be positive infinity or negative infinity? If you put in a very big negative number, would your answer be a very big negative number or a very big positive number? It would be a very big negative number. Now, if you were to graph this from last semester, if you were to graph this, an x cubed graph with a vertical stretch by 5 looks like this. And as we go this way, as x gets very big, you can see that your y values get larger and larger negative values. So we can sort of generalize some things. If r is a number bigger than 1, and you go to positive infinity, in other words, you'd have all positive numbers, can you see that this would just get bigger and bigger and bigger in all cases? We can't make a generalization to negative infinity because it would depend whether r is even or odd. I guess we could make some limit as x goes to infinity. Oh, I wanted to do negative infinity. Negative infinity of this if r is bigger than 1 and our r value that looks like ris. Not happy. There we go. Proper use of spacage. I don't know if spacage is a word. If r is even, what happens to any negative value if you have an even exponent? It would become positive. And if r is greater than 1 and r is odd, ooh, okay, I need to work out a few more things on the first one. We'll keep it like this to start with, and then we'll look for problems. The limit as x goes to negative infinity no, this is okay. I'm okay with this. Because if I say even, can you have a decimal? Are there even decimal numbers? It's like 2.3. Is that even or odd? That's a good question. It's not really either, is it? Where do decimals fit in? Even, odd, and maybe there's a different one? Weird? I'm not sure. But even and odd tends to mean whole numbers, so I think we're fine. The reason I wanted to talk about decimals is you can't have x go to negative infinity if you had x to the half or 1.5, because then you would be taking a square root of a negative. But we're not going to worry about that right now. So we get some generalizations. We think about, well, what happens in the general situation? And as x gets really big, for most of these, you don't need a general situation. You can just think about the context and wonder, well, what is going to happen? So now we start looking, well, what happens if the value's on the bottom? What would happen if you plugged in a very, very large number and you had 1 over that number? What's 1 over 1,000 get close to? 1 over 1,000,000? 1 over 1,000,000,000? As you get closer and closer and larger, we would say that this is equal to 0. I'm not sure if I have it later on in the notes, but I want you to think about this one. And then I want you to think about these are such good examples. I probably have these same examples later on in the notes, but these are some ones to think about. What happens when n gets close to 0? Okay? What happens when you divide 1 by a very, very small number? It gets very, very big. So an idea might be that this should be infinity. Again, your textbook will just say does not exist, so you won't get into this little interesting point of view in this situation. This one goes to infinity, and this one truly does not exist. What's the difference? One of the things that we learned the other day when we looked at piecewise functions is that a limit only exists if it approaches the same number from the left side as it does from the right side. And so if it's approaching the same number from the left and the right, we would say that it exists. What does the graph of 1 over n look like? It's a reciprocal graph. You have an asymptote at x equals 0. You have an asymptote at y equals 0. and your graph looks like this. Now, from this graph, we can see the first answer, the limit as n goes to infinity. As our values get really, really big, the green graph gets really close to 0. The second one, as n gets close to 0, can you see from the left it goes down to negative infinity, but from the right it goes up to positive infinity. So since one side is going to negative infinity and the other side is going to positive infinity, we would say that the limit does not exist. But in the second one, if I would draw this graph, it once again has a non-permissible value, can't have 0. It has an asymptote at y equals 0 as well. In grade 11, your teacher might have called this the volcano graph, because it kind of looks like a volcano with asymptotic lava spewing out the top. But on this one, when you're going from the left or from the right, both branches are going up towards positive infinity. So we would say that the limit as n goes to 0 in the second one is infinity. What happens when you plug in a very, very large negative number? Well, the only place that we have an n is right there. What is 1 over negative a billion? Really, really close to.
Hi, sorry to interrupt.
So as n gets to be a very, very large negative number, 1 over a billion, does it make sense that this is going to get close to 0? And then your thinking has to be, well, what's the overall limit of this whole thing? What's 5 minus nothing? What's 5 minus close to 0? It's going to end up being close to 5. So we can summarize some of these patterns. If your x value is getting to be really, really large, and yes, does yours have n's and mine has, no, this is, do we have different letters? Yeah. Are you okay with the different letters? Can you, no? Okay, well, I have some therapy things. It'll be worked out just fine. Yeah, in yours it has n's and mine has x's. But we're okay. And that if x gets really, really big and you have a really, really big number in your denominator, then that limit is going to go to be 0. Another thing that you looked at when you started to graph these functions in the past, 2n plus 3 over n, you said there's going to be a horizontal asymptote in this situation. Do you remember how you found that horizontal asymptote to be at y equals 2? Did you have any strategies? Yes? No? Well, one of the things that we're going to do, first of all, I'll show you the proper technique of how you could show it. But you could factor out the highest power out of your numerator and your denominator. So if I did that, I would still get the limit as n goes to infinity. Factor out an n here, leaving me with 2 plus 3 over n. And factor, well, there's nothing to factor out on the bottom. But then my n's would simplify. And this question that I initially started with is the same as this question. And we already know if the denominator goes really, really close to 0, I mean, if the denominator gets really big, then that 3 over n is going to get really, really close to 0. And in that case, this limit is going to equal 2. Now, that being said, if you start, once you start getting good at these, you can just tell by looking at it. What you can do in a situation like this is just ignore everything but the highest power. The highest power in my numerator is n to the 1. The highest power in my denominator is just an n. If I just look at that, so in other words, I just look at the 2n and I just look at the n, what does 2n over n simplify to? If you ignored everything else, the 2n over n would simplify to n, to 2. And you can use that, will always also work as a way to figure out what the limit is, instead of showing all the work with the factoring. The factoring works, but I could see right away that the limit was going to equal 2. And you might remember drawing those horizontal asymptotes from graphing in the past, that you would have that value at y equals 2, and then you would know that your graph approaches that as the x value or n value gets larger and larger. So what I'd like you to do on this one is look at it and take a stab at what you think is going to be the value of this limit just by looking at it. Then do it again by factoring it out to check to see if it worked. So our strategy for the factoring is you look for the highest power, factor the highest power out of both the numerator and the denominator. It will simplify, and then you can work from there. So just by looking at it, if your guess was -3/8, you are correct. Why is it -3/8? Because n cubed is the highest power, and the number in front of n cubed in your numerator is -3. The coefficient of n cubed in your denominator is 8. Now looking at our technique, if we wanted to show why this worked, you could factor out an n cubed out of your numerator, leaving you with 1 over n minus 3, and an n cubed in your denominator, leaving you with 8 plus 1 over n cubed. Well, your n cubes would simplify. And the limit as n goes to infinity of 1 over n minus 3 over 8 plus 1 over n cubed. Can you see that this would go to 0? This would go to 0. And what are you left with? You're left with -3 in your numerator and 8 in your denominator. Now, both of those examples looked at situations where the numerator and the denominator, the highest power, was the same. So I'm going to just add some examples. Limit to be other situations. What would happen if I had 3n squared plus 5n to the 4 over 7n cubed minus 8n to the 9? Right? How do I know just by looking at this the answer to this one's going to be 0? Yeah, the n to the 9 is in the denominator, meaning that in the end, this is the most powerful thing in this function. The higher the exponent, the more powerful it is. It's in my denominator, so I'm going to end up with a much larger number in my denominator than I will in my numerator. And as a result, as n gets really, really big, this will get close to 0. You could do the technique to find out that that's true. What's the highest power in the whole thing? An n to the 9. Factor an n to the 9 out of the top, factor an n to the 9 out of the bottom. You will get 3 over n to the 7 plus 5 over n to the 5. 7 over n to the 6 minus 8. The n9s would simplify. These would all go to 0. And so simplifying it would give you 0 over negative 8, which ends up with 0. Okay, again, you could see it just by looking at it originally. So that's what happens when the powers aren't the same. I can make a similar one. I can click, ready, yes, okay. I can make a similar one, limit. Ooh, we should just so we don't get too fixated, we should use other letters just for fun. Should we go with k this? Ooh, k. K to infinity. Does it make it harder when I switch the letters? It's not supposed to, but for whatever reason it does. You get used to x's and you're like, I'm good. Or you get used to n's, and then you switch to a k and you're like, can't do it. Well, we can do it. Limit as k goes to infinity. Negative 3k squared plus 5k to the 5 minus, ooh, that's a k. Minus k to the, minus 3k to the 7, why not? Over 5k to the 4 plus 3k. It's hard to make a k after you've been making x's for a long time. K to the 6. That last k was almost a fail. It's looking mostly like a fail. So I look at this, and I can tell just by looking at this that the answer is negative infinity. How can I tell that? Well, my highest power is right here. As I put a very large number in for k, can you see that that's going to be a very large negative number because of the negative 3 out in front? We can show this as well. Limit as k goes to infinity, I could factor out my k to the 7, leaving me with, ooh, no, this is good. This could be a good question. I think it's going to be, yeah. Negative 3x squared becomes negative 3 over x to the 5 plus 5 over k squared minus 3 over 5 over k cubed plus 3 over k. These will simplify away. This will go to 0. This will go to 0. This will go to 0. And this will go to 0. And something that I think is important to notice in this situation is that as k goes to positive infinity, this will go to 0, but will be a positive 0. And this will go to 0 and be a positive 0. Because if I went to 0 and it was a negative 0 on the bottom, then a negative divided by a negative could become positive. Does that make sense? Because in the end, on the top, I'm going to get negative 3 divided by 0. And negative 3 divided by 0 is either going to go to positive infinity or to negative infinity, or in different directions depending on what we have. But in this case, since my 0 on the bottoms are always going to be positive, it will equal negative infinity. But I think this one's easier just to see that the most powerful thing here is a huge negative number. If I ignored everything else, I can say, yes, this is going to go to negative infinity in the end. In fact, the methodology itself, I think, adds more confusion than just saying, what's my biggest power? What's my most powerful thing, the k to the 7, and what will that go to? That'll go to negative infinity. Find the limit if it exists. So as n gets very, very big, what happens to this function? If you put in 100, what's negative 1 to 100? I know 100 is not super big, but we'll start in small. What's negative 1 to the exponent of 100? 1. What's negative 1 to the exponent of 101? Negative 1. And then it jumps back to 1, and then to negative 1, and then to 1, and then to negative 1, and then to 1 and negative 1. Can you see it flip-flopping back and forth forever? And that's just looking at the whole numbers. It gets even messier if we go into the decimals. But if you just think about the whole numbers, you can see that it flip-flops between negative 1 and 1. And so we can't say that this ever goes to a specific number. And in this situation, we would say it does not exist. Ooh, I'm going to take out some grade 11 formulas for you for this next one. So first of all, this idea, 1/2 to the n. If it's 1/2 squared, it'd be 1/4. 1/2 cubed would be 1/8. As you get bigger and bigger and bigger, can you see that this is using your exponent rules? This is the same as 1 over n and 2 to the n. You could put that exponent to both. And 1 to any exponent is still going to be 1. And what happens to our denominator here as n gets really, really, really big? You're going to be dividing by a really, really, really big number. And we would say the limit is 0. And so we could say in general that if you had any fraction in here that was less than 1, that you end up having a limit go to 0. Now you've seen this before, and you saw this kind of without the proper terminology in grade 11. In grade 11, you had geometric sequences. So for example, you would have something like 10 plus 5 plus 5 halves, plus 5 quarters, plus dot, dot, dot. Can you see that I'm multiplying by a half each time? If you wanted to add up the first 10 in this series, you had a formula. You had a formula that said the sum of the first 10 is equal to term 1, 1 minus r to the n over 1 minus r. Did you have that formula memorized, or is this the first time you've seen it since grade 11? Memorized. Perfect. Okay? You also, so this formula, if you wanted to find how much you added up the first 10, you could say the sum of my first 10 would be term 1, which is 10. 1 minus, I'm multiplying by a half each time. You could plug that into the formula, multiply it all out, put it into your calculator, and boom, it would add up all those numbers for you. That's just wonderful. Now, you also had a formula, switch, saying that in some cases you're allowed to add this up forever. And you learned that you were only allowed to add it up forever if your common ratio was less than 1, positive or negative, in between -1 and 1. Are you okay with the absolute value less than 1 meaning the same thing as between -1 and 1? Now, you wrote down your formula from grade 11. We found out it was like this beautiful formula, whereas the other formula was big and ugly and complicated. The infinite formula ended up being quite simplistic. Well, what was happening? What we were really doing is we were taking this and saying, what's the limit as n goes to infinity of this whole thing? Well, we just replaced the n with infinity on the left-hand side of the equation. And then we said to ourselves, if I had a half in here to the exponent of n, and n gets really, really big, this limit goes to 0. And that's the only thing that changes. And so what's left of my formula, just term 1 times 1, ends up being term 1, and 1 minus r in the bottom. So in grade 11, as a math teacher, you're trying to explain that if n was really, really big, this is basically 0. You're getting to the idea of a limit without using those words. But that's where the sum to infinity formula is. And we could, if we wanted to, add up all those numbers forever and get 20. Which is a lot easier to add up an infinite amount of numbers than it would have been to add up the first 10. Which is kind of interesting. Kind of doesn't make sense that it's easier to add up an infinite amount of numbers than it is to add up 10 numbers. But in this situation, it is. And it ends up being a nicer number adding up an infinite amount of fractions than adding up 10 fractions. Oh, and I did have it. We did this one already. See, I said it was going to come up. But I changed the letter to an X. This is the one that we did before, where if you graphed it, 1 over x graph looks like this. And if you go from the left and if you go from the right, as you get closer to 0, one side goes to infinity, one side goes to negative infinity. Since the left and the right are not the same, we would say this does not exist.